This is ScoreBooster Chemistry video lecture 36, and our topic for today is going to be on the introductory part of structure and general properties of nonmetals. Don't forget that we have gotten into the section of another broad concept, that is physical chemistry, inorganic chemistry. And from the introduction of the inorganic chemistry class, we said we are going to be talking more about metals and non-metals. Basically, the metals, those common ones like sodium, like potassium, like calcium, magnesium, aluminium, and their compounds, how to prepare them, their occurrence, and their physical chemical properties, the way they react. Then we said we are going to move into the concept of non-metals. Non-metals, we talk about some non-metals, their compounds, how to prepare them, and their occurrence, their structure, and every other thing that we need to know about them. So we have talked about metals in general, although we have not talked about specific metals in detail. We are still coming to that. So this lecture is going to serve as an introductory class for what we should be expecting, just give us a glimpse or some ideas about how nonmetals, what nonmetals are, especially the common ones like carbon, like phosphorus, like sulfur. So when we talk about the nonmetals in detail, we are going to talk about the hydrogen, we're going to talk about chlorine, we're going to talk about oxygen, like that. We have talked about semi-metals the other time. So at the end of today's class, our aim is just one. We should be able to describe structures and properties of some nonmetals, although as we are going to learn later, nonmetals do not have a well-defined structure like we have in metals. So that is why we say structure and properties of some nonmetals. So as we are going on through the course, we are going to talk about each of these nonmetals in detail. That is when we'll be able to describe the structure and properties of each of them in detail. So as a matter of introduction, this is our periodic table. Nonmetals, they are just like 2% of all the elements in the periodic table that they have discovered so far. We said this left part and this down part, the actinide and antinide series, contains metals. These red lines, this zigzag red line, is the demarcation between the metal and non-metal. An element close to this red line to the right, like boron, like germanium, like astatine, like tellurium, these are called metalloids, semi-metals. We have talked about them. So at this far right from carbon here, this up to this group 0, they are non-metals. They are almost 17 in number on the periodic table, and they are very, very important, as we are going to see, especially this carbon in group 4, nitrogen, phosphorus in group 5, oxygen, sulfur in group 6, fluorine, chlorine, bromine in group 7, and all these noble metals in group 8 or group 0. As we are going to see later, they are very, very important. So now we have talked about location of them. Now, physical properties. Like I said, they are 17 in number in the periodic table. Physically and under normal conditions, at room temperature, more than half of them are gases. Only one is a liquid, and that is bromine, and other ones are solid, like copper, and solid like carbon, like phosphorus, and others like that. They are solid. So ordinarily, majorly, they are gases at room temperature, although those that are liquid or those that are solid, any reaction can happen to them or any process can happen to them that we can change their state of matter. But that is not what we're talking about. We're talking about at room temperature at ordinary condition. So the non-metals exhibit a rich variety of chemical behaviors. Like I said, in metals we have organized structure that we can use to describe metal. But this in non-metal it is not like that. They have diverse way of behaving in such a way that the property of maybe a particular one cannot be used to generalize for the property of other, even if they are in the same group or in the same period. In the non-metal, we have the most reactive element, that is fluorine. I mean fluorine F, not chlorine F, the number 9 element. Then we have the least reactive of all the elements, and those are noble metals. You can see that they have diverse way of behaving, or chemical behaviors, and they form many different ionic and covalent compounds. So why they have this diverse behavior is because of their electronic configuration. Some have completely filled p shell, some have partially filled p shell, and again some have d shells that are not filled, especially this astatine. It has these shells that is not filled. So we expect these differences to occur during chemical behavior because of changing the way the electrons are arranged. You know, sometimes when you have something like that, especially on the D shell, you can have overlapping, you may not have overlapping. So when you have something like that, we expect some chemical behavior. That is why non-metals have different way of behaving. So the following are just the general properties of non-metals. The first one is high ionization energies as compared to metals. During our discussion periodic table said ionization energy increases across the period and decreases down the group. So if you take any period now as a case study, like period 2 now, where we have lithium, we have beryllium, up till fluorine and neon. So the ionization energy increases from lithium up to neon. So since that energy increases, it means those non-metals have higher ionization energy than the metals. And again, under each period, ionization energy of one element is higher than the ionization energy of the one immediately before it. Like now, if you have carbon and nitrogen, ionization energy of nitrogen is more than carbon, because carbon is just one element away from nitrogen and they're in the same period, even among the non-metals, I mean. That is why they don't lose electrons. They have high electronegativities. High electronegativities means they can gain electrons easily. That is why they are all the time they are anions. They form anions during reactions. They form anions because they don't lose electron, so they gain electron. So the higher the value of ionization energy, the higher the tendency there is of which they can gain electrons. Poor thermal conductors. Yes, they have poor thermal conductors because in their structures, as we are going to see later, it consists of covalent bonds normally. So they form molecules, they don't form ions. So we expect them to be poor conductors of thermal and electrical, poor conductors of thermal and electricity. We said majority are gas, some are volatile liquid, like bromine now. Others are solid. Those ones that are solid are brittle. They are not strong because they consist of molecules. They don't consist of ions. They are not strong, so they are not malleable. They are not ductile. You can't play around with them. they are brittle and they are not strong. They don't have metallic luster. The lusterness is because of the way they are arranged. They jam-packed each other in a way that you cannot explain the structure. So they don't have luster. They gain electron easily. That is what we said here under electronegativity, but we just need to repeat it once again because somebody might have forgotten what electronegativity means. They are dull and they may be colorful sometimes, like bromine, like iodine, they are colorful, but ordinarily they are dull. If you see them, they are dull. Like in carbon now, carbon is dull because it's black. So they don't have, they are not always shining like that. It is only if something has happened that has transformed them, like in diamond now, as we're going to see later, that you can expect something like shining color, a shining appearance in them. So let's go to the structures of nonmetals now in general. The structures of nonmetals differ dramatically from those of metals. Yes, we have talked about that. Metals have correct structure, they have well organized structures, but in nonmetals you can have something like that. Metals crystallize in closely packed arrays. That is what we said. In crystal structure, you have the arrays of all the elements in a regularly and repeating pattern. But in nonmetals, you cannot have that, because in their bond, they have covalent bond and they have individual molecules. You can't have a concise or a definite arrangement of the molecules among themselves. Those electrons in the nonmetals are localized in a covalent bond because they cannot move this. Because they are not conductors, they are localized. They are just somewhere, just spinning. They can't move around. That's why they are localized. They can't conduct electricity in that case. So whereas in a metal, there's delocalization of the electron throughout the solid. So when there's delocalization of electron throughout the solid, the electrons are free to move around. That is why metals are able to conduct electricity. So those are just small differences between metals and non-metals in their structure. The strength of the bonds dictate the types of molecules they form. Sometimes you have diatomic molecule, you have monatomic molecule, you have polyatomic molecule. The structure, the bonds they form. If this is tetragonal, is it trigonal, is it single bond? That dictate the strength of those electrons. So when you have 3 bonds now, like in nitrogen now, you expect something like 2 sigma and 1 pi. Some have also just 1 pi, some have just 1 sigma, due to overlapping and the way they do. That is under hybridization. As I've said, we are going to talk about hybridization later. So if you understand hybridization very well, you are going to understand why some are strong and some are weak. But for now, what you just need to understand is that they have diatomic molecules, monatomic molecules, and just some have polyatomic molecules, like in sulfur and fluorine, like we're going to see later during this lecture. So if you look at carbon now, this is diamond. You can see it is shiny. Carbon occurs in elemental state in many forms, because in the H cross you can see carbon. So in elemental state you can see carbon in form of graphite, you can see it in form of diamond, in form of carbon black, in form of graphene, even carbon nanotubes. That is just discovery of recent. So if you look at this diamond, if you look at this graphite, this one is black, and you can see the structure is not regular. It means it is not strong like that. This one look like ornament, like ring, I mean like earring. It is fine in nature. It is. So the process that form the two of them, we are going to talk about it later, but just know that the two of them are just forms of carbon. They are in different physical states, and that phenomenon is what is called allotropy. Allotropy is when you have a single element that can exist in 2 or more different forms, I mean physical state. So this is the structure of diamond is here. This is the structure of graphite. If you look at the structure of diamond, each of the diamond here has two elements, two other carbons. It means we have tetragonal arrangement. So this tetragonal arrangement now is responsible for the strength of diamond. You know that diamond is very, very strong. In this case, we have triplanar arrangement, trigonal. So carbon has 4 electrons in the atmosphere. Don't forget, carbon is the 6th element, so the electrons in the atmosphere is just 4. So here now, it bonds with 3 carbon atoms. So definitely there is one other remaining electron. That remaining electron is that remaining electron is what is inside the structure. Each of them contributing one electron to form something like electron cloud. That electron cloud is what is responsible for the conduction of electricity that we know graphite to be able conductor of electricity that we know graphite for. Unlike in diamond, that's closed structure. So this tetragonal arrangement makes diamond to lack mobile electron, and hence diamond do not conduct electricity. Diamond is a very hard crystalline material that is colorless and transparent when pure. It forms the diamond molecule. Diamond molecule is what I've explained. You have tetragonal structure. Carbon forms with 4 other carbons. Each of the carbon now forms 4 other carbons, and that is extend throughout the structure of the carbon. So diamond is able to form that giant structure with no free electron inside. Unlike that, graphite is a very soft material, very slippery. Even if you look at this structure, you can see that it's not hard, because the end here is not smooth. Something has taken something away from it. So the same way in this place, it is not smooth. Something has taken something away from here. So we expect that this material is not strong, because had it been strong, nothing will be able to take away its part unless something that is more stronger. So here now, because of the diamond molecule that this one can form, nothing in existence is very, very high. Nothing in existence can break this structure of diamond. So graphite can conduct electricity, as I've explained. It has mobile electron in the structure. That the mobile electron is the factor that is responsible for its ability to conduct electricity. So let's now go to phosphorus. Phosphorus is that name is from a Latin word. It means light glowing. When something gives light, that is what is called phosphorus. So during the early discovery of phosphorus, the isolation of phosphorus brought light. That's why they name it phosphorus. So in the dark, it glows. You see something like light when you see phosphorus in the light. In the dark, I mean, it glows. So when you now expose it to the atmosphere, it burns. So it glows in the dark and it burns in the air. So that is what they call it, light glowing. So it does not occur in uncombined form. In fact, that is the only element that does not occur in uncombined form. It has 2 allotropes. 2 allotropes, don't forget I've explained allotropes. So 2 allotropes of phosphorus are white phosphorus and red phosphorus. So we are going to explain that one now. So white phosphorus is white in color, as the name implies. It melts at 44.2 degrees C and boils at this temperature, 280 degrees C. It is soluble in water, to which it is kept, because we said when it is exposed to the air, it burns. So because of that, it is being kept in water. So it is insoluble in water. So it is safe to keep phosphorus in water. Is safe, because if you expose it to the atmosphere, it will burn and will not be useful again. But any attempt to make contact with carbon disulfide, it forms soluble compound. So it is very, very reactive and toxic. We said it's very, very reactive and it is very, very toxic. So it is not safe to work with white phosphorus, it is not safe to handle white phosphorus. On the other hand, if white phosphorus is heated between 270 and 300, don't forget we said 280 is the boiling point of white phosphorus. So if it is heated to between 270 to 300 in the absence of air, then there is going to be a phase transformation, and that phase transformation will give us what is called the red phosphorus. The red phosphorus is the other type of phosphorus, the other allotrope of phosphorus that is denser than white phosphorus. It has a higher melting point than white phosphorus. Don't forget, we have heated white phosphorus and it has transformed to red phosphorus. So red phosphorus now has a higher melting point at around approximately 600 degrees C, and is much less reactive than white phosphorus. It is less reactive. It is unlike white phosphorus that is more reactive. It is essentially not toxic. It is non-toxic material. It is easier to handle than is for white phosphorus. So in phosphorus we have PP bond. Phosphorus and phosphorus atom are combining with one another in a single bond. It is single bond. Don't forget, phosphorus is the 15th element in a periodic table. You should be able to write the electronic configuration correctly and be able to draw it how they can combine with each other. Each of the molecules of phosphorus contain 4 elements. P4 is among the polyatomic phosphorus. So because of the 5 electrons in the outermost shell, so 4 of these elements can combine. When they combine, they donate electrons that each of them now share to contain to complete the outermost shell. Don't forget, when we have 5 electrons in the outermost shell, each of these atoms can donate 1, then 3 others will donate 1 each. So from plus the 1 that this first one donated, making 8. So phosphorus can complete the outermost shell. That is why phosphorus has 4 electrons. Each time it has 4 elements in the outermost shell. That is during covalent bond. It has 8 electrons. It has completely filled shell. So it contains 4. So the summary of it, the lesson of this is that phosphorus in its molecular form is not diatomic, it's not monoatomic, it is polyatomic, because each of it contains 4 phosphorus atoms combined together. That is just the brief summary. It is tetragonal, because when you hear 4, you know it's tetragonal. So it is tetragonal, like in carbon, it's also tetragonal. So let's go to sulfur to complete our discussion today. The allotropy of sulfur is far the greater and more complex than that of any other element. It is very, very diverse in nature. Sulfur is very, very abundant in nature. Even the recent research shows that in the atmosphere of Venus and in the ionosphere, I hope you remember what ionosphere is. That is another layer above the earth here. So that ionosphere, the majority of the compounds there, the element there is phosphorus, although in various allotropes. So phosphorus is very, very diverse in nature. It's very, very abundant in nature. So the most common allotrope of sulfur is rhombic sulfur. We have like 3 allotropes. We have the rhombic sulfur, the monoclinic sulfur, and the prismatic sulfur. Each of these sulfur allotropes is named according to its shape or shape of the crystals. So if you have the shape of the crystal, you can name the sulfur. So in the case of rhombic sulfur, now the shape is like a rhombus. In the shape of prismatic sulfur is like a prism. So That is how it is being named. So the color of the rhombic sulfur is yellow. It is very common. It is very stable. So rhombic sulfur is the form to which all other allotropes revert to at room temperature. So sulfur at room temperature is rhombic. So many people have seen it before. If you see yellow sulfur, so it is rhombic. At room temperature, all allotropes of sulfur convert to rhombic sulfur because it is very stable, and at room temperature it occurs like normal sulfur. So the crystals of sulfur melt at 113. So if you heat that rhombic sulfur to 113 degrees C, you are still in the range. So after 113 like this, it begins to melt. So if it begins to melt, so that means it transforms to another allotropes of sulfur. Don't forget, in phosphorus we said we have red, we have white. So heating white to between 270 and 300 giving us red. So it's same thing here in sulfur. If you heat rhombic sulfur to 113, then you get another substance. So if you now cool it, because after melting it's going to melt, it's going to become something like a molten form, is like a liquid. So if you now cool this liquid, it gives something. That thing look like a needle. So that needle is called monoclinic sulfur. So it is stable and it converts itself to monoclinic sulfur. So you have it stable at between 96 and 119. So after 119, that is when it converts to another form, that is prismatic sulfur. So at room temperature, then this one reverts back to rhombic sulfur. So don't forget, we said is the most stable, and that is where all other allotropes of sulfur revert to at room temperature. Both rhombic sulfur and monoclinic sulfur contain sulfurate. That's what they call it, sulfurate. It contains S molecules, in which atoms form 8 members, puckered ring that resemble a crown. If you see this, unlike in phosphorus that we have 4, this one is 8. See, 1, 2, 3, 4, 5, 6, 7, 8. So if 8, so this one is also 8, this one is 8, this one is 8, like that. So the molecules of sulfur is 8 all the time. So each sulfur is bonded to each of its 2 neighbors in the ring by covalent sulfur bond. In the phosphorus, it is phosphorus single bond. The sulfur, it is sulfur single bond. So in sulfur it is 8, and in phosphorus it is 4. That is just the lesson of what we are trying to say. So thank you very much for listening. But before we go, let us try to look at a quick review. Carbon has various allotropes. The common ones are graphite, diamond, charcoal. In fact, they have discovered another one in the US that is called fullerene. We are going to talk about that when we get to carbon. Diamond is strong, while graphite is slippery. It is not strong. Phosphorus has 2 main allotropes. We have the red one and the white one, with each transformed into the other. Sulfur is very abundant and has complex allotropes. We have the rhombic sulfur, the monoclinic sulfur, and the prismatic sulfur. So the beautiful things about this is that you can transform from one form to another, especially in phosphorus and sulfur, but in carbon you cannot transform it. We are going to talk about each of these later. In carbon, you are going to see how it is difficult to transform from one form to another. But each of these allotropes, each of them has a very good application to which they can be subjected to. That is why it is worthwhile to give it a thorough detail of study, and hence we are doing that now. And again, in forming these compounds, don't forget we said they are molecules. They contain covalent bonds. So each atom can combine with another atom to form molecules. So in carbon, it is single molecule, single atom. In hydrogen, it is diatomic molecule, so two hydrogen atoms combine. In oxygen, the same thing. In nitrogen, is the same. In phosphorus, it is 4. In sulfur, it is 8. Those are the things that we just need to learn today. Hope the short lecture is understood. So if that is the case, let us meet again on hydrogen and its compound with sample questions and solutions. We did not have question on this one because it's just simple introduction of the concept we are going to enter deeply later. So we will talk about more questions and solutions when we get to each question pertaining to each element and their compounds that we like to talk about. Thank you very much for listening, and don't forget to share and like our videos.